this is amortized constant complexity. So this is a talk about runtime complexity, but we all know this. This is easy. So what is amortized complexity? Let's check the literature. So you might want to consider the classics here, but Ahu actually doesn't have anything on the topic. You might check CppNorth, but it also doesn't have anything on the topic. Then there's this paper by Robert Tarjan, but that's kind of hard to read. So let's check Corman. And they fortunately have a full chapter on amortized analysis, so let's go with that. So they list 3 different methods, and we are going to go with the accounting method because that's obviously the coolest of the 3. So what is accounting all about? Coins, it's about coins. So the idea here is that we use coins to represent the cost of the computation, and then the number of coins that we need gives us a measure for what the complexity is. So let's set up a little vector, and now we're going to push back some elements into that and look at the complexity. So I'm pushing back 1 element. I need to pay 1 coin for copying the element, and then the element is in there. I push back another element. Again, I need to pay 1 coin for the copying, and that's it. Now, when I want to push back the 3rd element, things get interesting because there's no more room in the vector, so I need to allocate a new buffer. And now I need to copy all of the old elements over to the new buffer. Each of that costs me a coin, and then finally I have to pay another coin for the new element that gets inserted. So what is the worst case complexity of this? Yeah, you guessed it, it's linear. Linear in the number of elements of the vector. So that means like our budget here for 1 element is actually 3 coins. I use 1 of those 3 coins to insert the elements, the other 2 I throw away. For the 2nd element, I now have a budget of 4 coins. Again, I only need to use 1 of those coins, the other ones I throw away. And for the 3rd element, I have a budget of 5 coins, and now I actually need all of those 5 coins to execute the operation. So I know what you're thinking. We've been throwing away a lot of coins here. That doesn't seem to be a smart idea. So what if instead of throwing them away, we could save them somewhere so that we could use them then in subsequent operations to pay for computation? And that's exactly the idea about the accounting method. So one important thing to notice here is that our account can never go negative, right? We can only spend coins that we actually saved from earlier operations. And now if we look at pushback, we actually notice something interesting because we are now able to do pushback when we follow these rules with just a constant budget of 3 coins per operation. So let's look at how this works. When I push back the 1st element, I need to pay 1 coin for copying the element. The 2nd coin I put on the element that I just inserted, and the 3rd coin I put on 1 of the elements that was already in the vector. I do the same thing for the 2nd element, and now when it comes to the 3rd element, you notice that all of the elements in the vector already have a coin on them. So I can use those coins to pay for the copying to the new buffer, and I don't need to touch my budget for this at all, so I can use that to insert the new element. And that's the idea behind amortized constant complexity. So yay! And we still have some time left, so let's do another one for good measure. So if you look at the standard, then it says for the ranges begin operation that it has amortized constant complexity. So let's look at how this works. So let's say I have a vector with a bunch of elements, and there's one particular element that I want to get to. So I'm using a filter view to filter out all of the boring zeros to get me to that interesting element. And now obtaining the iterator to this, of course, has linear complexity because the filter view will have to skip over all the zeros until it gets to the interesting elements. But the filter view also has memoization. What that means is that the first call to begin is actually going to cache the result, and then if I do subsequent calls to begin, they're able to return just the cached result in constant time. So let's do the amortized analysis for this. So I start out with this vector with 1,000,000 elements, and then I have to pay 1,000,000 coins to iterate over all the zeros, and yeah, that actually doesn't work. But accounting is stupid anyway, so let's do aggregate analysis, right? So yeah, aggregate analysis, it turns out that for the case where I only do 1 operation, it also fails. And same for the potential method. But hey, I hear you say, like, we don't care about the case of only 1 operation because runtime complexity is about the asymptotic case. Well, unfortunately, this one, when it refers to asymptotic, it refers to the length of the input. But for the amortized analysis, I still need the upper bound to hold for all possible sequences of operations, including the ones that only contain a single operation. So yeah, despite what the standard says, those 2 are actually not the same. Thank you.